It's differentiable, which I'll just abbreviate DIFF. It's differentiable on the interval from -infinity to 2 plus the interval from 2 to infinity, which basically means it's differentiable everywhere except for 2. Okay? Another important theorem is that differentiability implies something called local linearity. Looks like a 3-year-old is doing the notes here. Differentiability applies local linearity. And I'm going to explain that with a couple examples. It's a really important concept in calculus, actually. So let's take a look at a couple of functions. First of all, let's look at absolute value of x plus 1. Okay, now again, let's go back to the calculator and analyze the graph of this. So absolute value of x plus 1, and here's what the graph looks like. Now, as you can see in this graph, there's a place where it's not differentiable, because there we can see a corner comes to a point. That's what we know that about the absolute value graph. And that 1 just moved the graph up 1, so that didn't change the fact that there's a corner right there. Okay. Now, notice what happens if I zoom in right on that point. Okay, so I'm going to zoom in repeatedly. So notice that I've still got that corner. Let me zoom in a couple more times and see if I can somehow get that to round out. It still looks like a corner. Oops. Zoom in again. Still looks like a corner. Now you can keep going if you want. The more you zoom in, it's still going to look like a corner. Okay, there's going to be a sharp point right there. Now, as opposed to another kind of function. Now, this one we would actually say this is not differentiable at 0, clearly. Okay. So now let's go back to another function. Okay, so that was my first example. My second example, let's use this function called g of x. Square root x squared plus 0.0001 plus 0.99. Just like that. Okay, so let's take a look at this graph. One, two, three, one. And then we'll add 0.99. Now go back to zoom 6, standard window. Notice the graph looks exactly like the absolute value graph that we graphed earlier. Okay? Now there's a difference though. Watch what happens if I zoom in on this one. Well, it still looks like a corner, just like the last one. Let's try it again. Now it still looks like a corner. Let's try it again. There actually is a point to this. Be patient. Actually is a corner. Oh, is it a corner? Zoom in one more time. Oops. Right there. Wait for it. Notice it's starting to round out. The more you zoom into this, it's not retaining that corner anymore. It's actually rounding out. And the more I zoom in, the more this is actually going to look linear. You can actually see there's this place where it seems to flatten out right there. Let's see if I can get it better. So the more I zoom in, notice how it's flattening out. We're not seeing that corner anymore. We're seeing the graph flatten out. So the more I zoom in, if I were to do this a couple more times, you would see on your screen eventually a perfectly flat line, which means that locally in the small neighborhood of that point, the graph looks linear. So the more you zoom in, the more it looks like a straight line. So that happens with graphs that are differentiable. If graphs are differentiable, the more you zoom in, the more it's going to look like a straight line. Whereas graphs that are not differentiable, that non-differentiability, that corner, that cusp, that vertical tangent, those will appear no matter how many times you zoom in. Okay? All right, so there's just some concepts about differentiability. The last thing we're going to do today is discuss something that your calculator does, which will estimate derivatives for you. Okay? So we're going to look at numerical differentiation. We're finding numerical derivatives. Now we talked about how that the definition for derivative came to be. It's basically a slope function where we take the limit as the 2 points come closer together. But one of the things that I know that we discussed in class was that if I had a function, I want to find the derivative of that point right there, the slope of the curve at that point there. Some of you suggested that maybe we can estimate that by picking a point slightly above, a point slightly below. And if we find the slope between those two lines, or those 2 points, that's basically the same as the slope of the tangent line to the curve. Okay? It's a good approximation for it. And the idea is the closer these red points are to the blue point, the better the approximation will become. Okay? And so in our definition, we actually take, if you take the limit as that distance approaches 0, that's where the definition of derivative comes from. But still, we can use this as an estimate. So when we talk about numerical derivatives, or to differentiate numerically, we're using this idea of picking a point above and a point below, finding the slope between those 2 points to estimate the derivative. Okay? Now the most accurate way to do this is by using something called the symmetric difference quotient. Hoping that the small case would be better, but it's not a whole lot better, is it? The symmetric difference quotient looks like this. The derivative at a particular value, we'll call A, is approximately equal to, okay, it's approximation, f of A plus h minus f of A minus h all over h. Actually, that should be 2h. Okay. Now, where that comes from, I'll come back to that formula in just a second, but let me explain the idea graphically. If you have a curve again, it's right here, and let's say this is the point, this is the x value where we want to find the derivative. So that's A. So what we do is we go a certain increment, we'll call h. We go h units above, which let's say right there represents A plus h. And if we go h units below, or on the other side of the point, we call this A minus h, then the slope between those 2 green points is going to be rise over run. Well, the rise would be the difference of the y-coordinates, and this is, the y-coordinate here would be f of A plus h. The y-coordinate here would be f of A minus h. Okay, so that's what you see in the top here. That's the change in y. That's your delta y. On the bottom, the change in x is this horizontal distance right here between these 2 points, which if it's h either side, if that's h and that's h, then the symmetric difference quotient has a 2h in the bottom. Okay? So anyway, that's a formula for approximating the derivative. Now, we've actually done this before numerically, so I'm not going to go through a specific example of this. But the point is to show you that your calculator is actually programmed with the symmetric difference quotient. Okay? So I want to go through an example of that. Now there's this particular syntax